Taylor polynomials. What is the equation of a line tangent to a curve at the point a, f of a? Well, we could use the point slope formula, and we'd have y minus the y from the point equals the slope, which is f prime of a, times x minus the x from the point. Now we could solve this for y by moving the f of a term over, and then call this p sub 1 a polynomial, and in fact a polynomial of degree 1. Let's look at this for a specific function. If we had f of x be the natural log of x and we're looking at a equal 1, we could figure out f of 1, and that would be the natural log of 1, which is 0. And we could also figure out the derivative, which is 1 over x, and that derivative at 1 would be 1. So we could put in those pieces. This would be 1. This would be 0, and this would be x minus 1, and we would have a polynomial of degree 1, which is a line that would be tangent to the curve at this point. And when we learned linearization, that it's an approximation for the curve if we're very close to 1. What if we extended this idea then, and we said, well, what about a polynomial of degree 2? Let's take our polynomial of degree 1 and let's add on a quadratic term with the requirements that this polynomial has the same value as the function at a, it has the same slope as the function at a, and it also has the same concavity as the function at a. So let's figure out what the second derivative of the polynomial would be. So first derivative, this would disappear. By the time we do a second derivative, this would disappear. First derivative would put a 2 out in front here, and then with the second derivative would just be a 1. So we would have 2c2 would equal our second derivative of our polynomial. We want that to equal the second derivative at the function at a, so we could put that equal and solve for our c2 and find that our c2 would need to equal 1/2 times the second derivative of the function at a, so that these conditions were true. So let's take that and put that in up here for our c2, and we see that our polynomial then of degree 2 would look like this. Let's take this and apply that to our specific example then. So we need to find the second derivative at a. So we had our first derivative was 1 over x, and our second derivative would be negative 1 over x squared, and our second derivative at a, and a was 1, so that would be negative 1. So we could put a negative 1 in here, and we would have our p sub 2, which is a polynomial of degree 2 that approximates this curve at a. And here is the graph, and we can see that it extends a little better approximation than the line, so we're looking right at 1, everything agrees, and we can move on a little bigger interval about 1 to have an approximation. Well, let's continue this idea and find p sub 3 by taking p sub 2 and then adding a cubic term with the requirements that the function at a and its derivatives up to its third derivative all agree with this polynomial. The p sub 2 will disappear taking 3 derivatives. So when we do the first derivative, we would have power out in front and decrease the power by 1. When we take the second derivative, we would have that power out in front, decrease the power by 1. And when we take the third derivative, we would have this. So we would need this then. It was our polynomial of degree 3. We would want that to equal our function third derivative at a, and we can express this as a factorial. We could solve this for c3 then by dividing by that factorial, and our c3 would be f triple prime of a over 3 factorial. So let's go ahead and apply that for our specific natural log function. So we had already that our second derivative was negative 1 over x squared, so our third derivative is going to be 2 over x cubed, and if we evaluate that third derivative at 1, we're going to get a 2. So we could put a 2 in right here, and then this is 3 factorial, which is 3 times 2, and we could cancel the 2, so it looks like we will have a 1/3 there. So here is our polynomial of degree 3. And what this is going to do is approximate the natural log around the value of 1. So let's go ahead and put that on our graph. We can see we've done a better job. Let's take off our first two approximations so we can see it a little better. And we can see that around a, which is 1, we've got a good approximation on an interval here. It looks really good up to this point here and really good up to this point here. And we extended that interval where it was a good approximation by increasing these degrees of these polynomials by adding on another piece to it. Well, we can generalize this idea to an nth degree polynomial. We could continue with this process, and as we saw the pattern, this would be the nth derivative at a. We would need all of the polynomial and its derivatives to agree with each other at a up to the nth derivative. And then because when we took derivatives we'd move this nth power out in front and decrease the power by 1 and continue, we would have that n factorial here when we solved for that coefficient. Now, if we build these polynomials, then the more that we add, the better we get of our approximation of the function. These are called Taylor polynomials, named after Brooke Taylor, who is an Englishman. He was a musician and a painter, and he did work in a variety of areas and research in a variety of areas, but his most famous was his development of ideas for infinite series and using these polynomials, and so they named them after him. Typically in math, it's not the person who discovered it, it's the person who then used it a lot in their work. So let's look at a Taylor polynomial defined. So if we have a function with n derivatives defined at a, the nth order Taylor polynomial for the function centered at a is, instead of using p sub 1, p sub 2 for polynomials, we're going to use t sub 1, 2, 3 for Taylor polynomials. And here is the formula that we essentially derived then, and remember that we need to have this polynomial agree with the function at a and agree with the derivatives up to n derivatives of the function at a. So let's go ahead and look at this idea of approximating a function with Taylor polynomials. Here we have the cosine function, and if we approximated that at 0 with a linear function, it would be this horizontal line, and that's a pretty bad approximation, just right at 1. If we increase the degree and we approximate it with a second degree polynomial, you see that we increase the interval on which it's a decent approximation. Now let's go ahead and do a third degree polynomial. And notice when I did the third degree polynomial, it didn't change, and the reason it didn't change is because a third degree polynomial, the x cubed term would need to be a 0 to make it a good approximation, so it didn't do so well there, so we didn't put that on there. But if we did a fourth degree polynomial, look, we're doing a better job increasing our interval here. If we do a fifth degree polynomial, notice we didn't have an x to the fifth term because it didn't improve our approximation. But if we did a sixth degree polynomial, now look at our interval here. We're doing much better at approximating it at an interval around 0. And if we did 7, we're not going to change it, but if we did 8, we extend that interval where we have that good approximation, and you can see then here is at 9 nothing but at 10. And so we increased our interval where this would be a good approximation of the function. Let's go ahead and take off all the others then and just look at, as you look here, you can see our Taylor polynomial. The 10th, we had our 0 terms for all our odd powers of x because that did not work to increase our accuracy for this approximation. And once we graph this, you can see how closely it follows the curve around a equaling 0.